believe it or not, we're actually nearing the end of all of our derivative work that we need for our AP test. So we are going to finish chapter 4, and then that's actually it for derivatives. So we just talked about optimization, some of those word problems of, maximizing, minimizing, things like that. The other application of derivatives is something called related rates. So these also are versions of word problems, and later we'll kind of mix them together to help you sort out which is which. But today is just the introduction day. So we wanted to do a video so that you could kind of pause, rewatch something, re-listen, explain. As you watch this, if you have questions, please jot them down, and we'll be able to, when we do, day 2 and 3 and 4 of all of this stuff, we'll be able to address those, excuse me, and get you that. So as you watch, kind of mark down questions as we walk through these, okay? All right, this first one, we use this example. It's just a very good example with talking through and introducing, and allows us to get a lot of the things that show up in related rates in a very easy, broke down format, okay? So here's our first example. So Phoebe is going east on Alamo Street. So here's Phoebe right here. Okay, she's going 40 feet per second. Now it's small here because this is kind of an older one that we use, but I'm going to put an arrow. So she is walking, to the east in this case, or going this way on there. So meanwhile, Kelvin is going south. So I'm going to put up that little arrow, and again, it's there. It's just hard to see. On Height Street at 30 feet per second. So Phoebe wishes to determine whether the straight line distance between them is increasing or decreasing. So these are different from related rates, because we're going to be looking for a rate. So how the distance between them is increasing or decreasing, that is describing the rate between them, versus like what's the farthest, what's the nearest, that's optimization, okay? So as we get into this and start looking at this, one of the very important things with related rates is time. So T, time is your independent variable. Okay, so we're going to have the, Phoebe's distance changing, Kelvin's distance changing, the distance between them changing. Those are all going to change with time. Okay, and that's the case in all of our related rates. Time is your independent variable. Okay, all right, so let's start breaking this idea down and look at number 1 here. So it says, let x be Phoebe's distance from the intersection. So you can see that x is denoted right here. Let y be Kelvin's distance. Write the rates that you know. Okay. All right, so when I go, I'm talking about rates. Rates are like speeds, velocity, those type of things. Well, I see for Phoebe here that we were told it's 40 feet per second. Okay. Now, I look here and I see that I've got this dy dt, dx dt, and it's like, what are those? Okay. Well, remember, dy dx meant derivative, which means slope. Okay. The only thing that changes, so if I look at dx dt, what changed is that now x is your dependent variable and t is your independent variable. So that's how the Leibniz notation sets up. The dependent variables in the numerator, the independent variables in the denominator. And we said that time is now always your independent, so that's going in the denominator. And then they just happen to use x. You could have put a here, b, whatever you wanted, m, it doesn't matter, but they chose x. Okay, so what dx dt represents is Phoebe's, because x goes with Phoebe's, derivative or slope, or in this case, it means her velocity. Okay, so this dx dt should be 40. I'm going to put units just for the sake of making sure we're reading through here. Feet per second. Okay. Now, Kelvin is y. So here's my y here for Kelvin. Okay. Kelvin's speed is 30. Now we're going to do something. We're not going to leave it like this, but here is going to be the one thing that we need to caution of. Kelvin his side is getting shorter, right? Because he's walking toward, like, it's getting shorter. Whereas Phoebe is getting bigger because this point is sliding out, and that's why those arrows were important. So we're going to have Kelvin's dy dx be negative because the change in his distance is negative. because y is his distance, t is time, and the change in distance is negative. So you're going to have some positive dy, dy dt, dx dt's derivatives, and you're going to have some that are positive. And pictures are going to be very important when we break down like the steps. You're going to want pictures because then you can put the arrows. Okay, is this side getting bigger? Okay, it's a positive. Is it getting negative? Nope, so it's a or is it getting shorter? Yes, so it's a negative. Okay. Now continuing 2 here, it says let z be the straight line distance between Kelvin and Phoebe. So here's that z right here. So write the symbol for the rate that we want, because that's what we want. Is that increasing or decreasing? All right, well if z is my dependent, t is time, what I want, here I'm going to slide down over here. Here we go. What I want is dz dt. That's going to be the thing we are looking for, because that's the distance between them. Okay. Let's process that a second here. All right, number 3, to find the rate you want, you need to write an equation relating the variables in the known and wanted rates. So in this case, what you know and want are x, y, and z. We'll get to the derivative, you'll derive the derivative. So when I look at my picture, I've got x's down here, I've got y's right here, I've got the z is attaching those 2 sides that are changing, and what I notice is it makes a right triangle. Okay, now it's not a perfectly drawn PDF that we scanned in here, but this is going north, so it does make a right triangle. And so an equation that relates those 3 variables would be x squared plus y squared equals z squared. Okay, oftentimes you get a Pythagorean theorem in there. Okay. All right, I'm going to go to the next slide. That kind of starts putting this all of this information now is going to start putting it together. Okay, 4 wants you to differentiate both sides. So I'm going to put my formula here again, x squared plus y squared equals z squared. In 3, and implicitly, and here's your key here, implicitly with time. So you are going to be doing more implicit differentiation here. Instead of having x's and y's mixed together, we're going to have a bunch of stuff, x, y, z, m, whatever variables you want, but we're going to take the derivative with respect to time. So time is my independent variable. Okay, so here's how it's going to look. So when I'm taking the derivative of x squared, I notice that I have stuff squared, so I would power out, power down, and then times the derivative of the inside, which is dx dt. Okay, when I take my derivative of y, that's still a dependent variable, so it's going to look very similar to this. I'm going to have to power out, power down, I don't need to write the 1. The derivative of y is dy dt, because time is my independent variable. That's the key of this whole thing. Equals, okay, well z's not time, so this is dependent on time, so it's a dependent variable. So I'd have 2z to the first, and then dz dt. Okay, so we're doing the exact same implicit differentiation, except t is your independent variable, and now you're going to have multiple. In this case, I have 3 dependent variables on time. So I have 3 things that are changing. Phoebe is moving, Kelvin's moving, and the distance between them is moving, and they're all moving with time. Okay, now in 5, this is where we start to actually solve something now. So it says when Phoebe is 200 feet, so Phoebe was x, so basically it's saying when x is 200, Kelvin, which was y, is 600 feet. At this time is a straight line positive. Okay, so you're given a bunch of stuff. So I was just given x. I'm going to start plugging in. I was just given x, so 200. Dx dt we said was 40. Oops, that's a 4 out of 9. Okay, that's what we had above. So then it says plus 2y, which is 600. dy dt, and be careful because that should be negative 30. Remember, Kelvin's distance is getting shorter, so his derivative is negative. Okay, and then equals to, okay, I don't know z, and I want to know dz dt. Okay, so this we talked about with this, like this is what we're trying to find, but I notice I still have z here. And so it's like, well, how do I, I've still got 2 variables because your derivative's a variable, it's something you don't know. Z is still a variable I don't know. What is going to happen 95% of the time here is using this X and Y, I can solve for this Z at this moment in time. So I was given, I'll write this moment in time. I was given the moment in time with Phoebe being 200 and Kelvin being 600. And so putting that into my Pythagorean theorem, I have 200 plus 600 equals Z squared. And then solving that gives me 632.456. Okay, which that is then going to go in for Z. So 632.456. All right, I'm going to slide down to the bottom and get everything all kind of plugged in here. I know I'm skipping, we'll come back to 6, but so solving this out, I would have, 2, so I'd have 400 times 40 plus, 1200 times negative 30 equals 2 times this number that I did have to find using my Pythagorean theorem. Or, I'm sorry, dz dt. Okay, so to solve, I would just divide this thing over 632.456. Okay, divide that over. And so this I can then enter directly in my calculator. These are definitely calculator questions. And I get dz dt equals negative 15.811 feet per second. Just a reminder, you need 3 decimals for everything. I suggest keeping more, even in this Pythagorean theorem. I probably should have kept more. You can store them in your calculator until the end. So, hit this, do that Pythagorean theorem, square root, keep that in the calculator, and then you can put it into your answer. Sometimes that works better. So going back to the actual question, it said, sorry about that. Okay, at this time, is the straight line distance increasing or decreasing? Well, I have a negative, so I would be decreasing. And then because it says at what rate, your rate is 15.811. Because you say it's decreasing, that's what takes care of that negative. So just be careful of how it's worded. If it just says what is the rate, then it's negative 15.811. If it has increasing, decreasing, and then the rate, that can be, but if you show your work, we're going to understand what you're going for. Okay. All right, so going to 7 here, list the things that we just did. So we're going to generalize this, and then we're going to do a couple more examples to, well, 3, I think, 3 more, to kind of help see this pattern. Okay, so here were our steps. Very first thing, and we didn't have to do it, but you have to draw and label your picture. There's going to be pictures for pretty much every one of these. I really can't think of one that doesn't off the top of my head, so you're going to have some pictures. Okay. The next thing is how I'll describe it is analyze derivatives and meaning, and you're going to want to make sure you write all of this down. And I'll model that. A lot of it was typed into that PDF thing that I had in there. So I'll model this on the next 3, but you're going to want to be very, very good with variables and labeling. And what do you know? What do you want to know? Because that helps you kind of see the path to get there. Okay. So number 3 then is to write the equation that relates the variables and not the derivative. The derivative, so in this case, my variables are x, b, and r. Just made up random things. So you would want something that relates those together. So you can see I put some examples here. You can have x, y, z's, radiuses and volumes and surface area. This is theta. You will get some about angles changing, like how does this angle change, things like that. So that's like a theta angle. Okay. After that, then you make sure you do your implicit differentiation. And so I put a question mark here because that's what's going to fluctuate. Like it'll be dx or dv or d theta dt. The dt is always there. That's always going to be your the thing that you're working, your independent variable. All right, 5 then, you got to start plugging in variables and your d, whatever you were given. And that, in this case, the one we just did, I had to plug it into the Pythagorean theorem to get what is my z side. I was given all my d thetas, dt's, but often you're missing one thing and you have to get it from another, I don't know if location is the right word, but another spot, and then solve. I guess would be step 6. So make sure you solve for whatever it's asking for. All right, if you need more time, pause this to write these down, and then when you're ready, hit play, and we'll start the 3 examples. All right, here's your next one. We have a 5-foot student, Cal, stands a distance x from a 12-foot pole. So here again, I'm going to kind of help with the picture at first here, and then I'll have you guys do it. This pole is vertical. It's just the picture's taken at an angle maybe. And then she has a shadow down here. Because I know my writing, I'm going to use H for shadow because my S's and 5s look the same, and I see there's a 5 right there. Okay, so her shadow on the ground is, again, I'm going to make this an H for everybody's ability to read my handwriting. So if Cal walks away from the lamppost at a rate of 14 feet per second, okay, as I read this, that's not labeled on there. So I'm going to want to do a couple of things when I put that on here. I'm going to put an arrow for walking away. So I'm going to say like, okay, my Cal girl here is walking away. So I'm going this to the right. Okay, I'm also going to want to write the rate with it. So it's 14 feet per second. The other thing, and this is one of the more important steps so that you can see that this is a related rates and you have implicit, is this change, is she's walking away from the lamppost. This is your dx dt. So I'm going to write dx dt equals 14. Okay, it's positive because she's walking away, so the distance is getting bigger. We're going to be looking, well, I'll get to the looking part here. So I know it goes with x because it's the walking away. I know it's positive because it's getting bigger, and since I have the x variable there, I know it's dx dt. Okay. All right. Now the other thing, before you can start solving anything, you need to know what are you solving for? So like what? I'll write finding. Like what are you finding? Because otherwise you just got a whole bunch of variables and numbers, and that doesn't make any sense. So if Cal walks away the lamp, what rate is Cal's shadow changing? Rate that the shadow is changing. So when I look at my picture, I remember that the shadow we labeled as H. I want the rate, so the rate of H is dH dt. This is what we're looking for. For all of these problems, when I help students, when I see, or suggestions when I take a quiz, you read the problem, you want to like write down large, like in the corner or somewhere, what are you looking for? Because otherwise you're going to get lost in all of the information if you don't know what you're actually looking for and have it explicitly written down for yourself, so that you know how to get there. Okay. All right, now on terms of like steps here, we said, okay, analyze the derivatives and their meaning. We did that. Write an equation that relates your variables. Now, in terms of variables, I've got x, I've got h, I have some constant. I have a 5 here and I have a 12 here. Okay, now this one's not as clear as like, okay, well, that's a bunch of weird stuff going on, and the picture is maybe a little misleading, but if I draw Cal and I draw this a little more vertical, my thing that relates everything together are similar triangles. Okay, and remember, similar triangles, your sides are proportional. That says proportional. Okay, so I'm going to set up some proportions for my sides. So for example, my vertical on my large triangle is 12. My base is x in this h, so it's x plus h, not times. So this is like the vertical and the horizontal. Now if I can say equals because they're going to be proportional, I can say, all right, my vertical is Cal, so she's 5. And then my shadow, my base, my horizontal is h. Okay. When you write this initial equation, there are not going to be derivatives in there. They're like, I didn't write this wrong because you're like, there's no dx, there's no dh. That's fine. You're going to get those by taking that implicit differentiation. Okay. Now, I don't want to take a derivative right now. I have like stuff in the denominator, and how do I do a derivative? So I'm going to cross multiply so that I do not have to do that. Okay, so cross multiply 12 times h, and I'd have 5x plus 5h. Even here, I'm going to simplify more. I have 2 h terms, so I'm going to subtract it over. Equals 5x. All right, now I can take my derivative because I want a dh in there. So derivative of 7h would be 7, and then derivative of h is dh dt. Okay, 5's derivative is 5. X's derivative is dx dt. now I'm looking for dH dt, so it's good I got one. But I also have this dx dt. Well, because I was thorough to begin with, I know that that's 14. It's written there for me. So I'm going to divide my 7 over. So I have dH dt is 5 times 14 over 7. 14 over 7 is 2, so this thing is just 10. Units, sometimes we'll ask you for them. They're not required, but it would be feet per second because that's what your 14 was in feet per second. Your lengths were in feet, so this is feet per second as well. All right, let's try another one. Okay, so I'm going to have you try to read this, draw the picture, and label, and then when you're ready, hit play and check it with mine. All right, so we have the top of a 13-foot ladder is sliding down a vertical wall. So I'm going to draw my vertical wall. Okay, I'm going to draw my ladder. Okay, I'm going to draw the ground to make my life easier. Here's my ladder. Here we go. And then it says it's 13 feet, so I'm going to put that on here. And it's sliding down the vertical wall. So I'm going to put an arrow signifying I'm going down. And my rate is 4 feet per second. 4 feet per second. Okay, when the top of the ladder is 5 feet, so I'm going to write the word moment here, that you are 5 feet above ground. Okay, because I can't, like this side is not always 5, so your moment in time can't be plugged in, and you'll see this again on the next one. It comes in later. Okay, so I'm going to write it over here for a second here. What is the rate of change of the distance between the bottom of the ladder and the wall? Okay. Now this one didn't tell me any variables. It didn't say put X here, or, the shadow is H. It didn't give me that. But everything that's talked about or given a rate, I need a variable for. So for example, this one that's like you're 4 feet per minute sliding down. So I'm going to say this is P. Okay. And then your distance from the wall to the bottom, okay, let's just make that B for bottom. And so I'm going to need a variable for that part as well. Okay, okay, what I'm looking for, like write that over here. I want the rate of that bottom change. So I am looking for dB dt. That is my goal. Okay, I'm going to do a little more unit stuff because I have this 4 feet thing here and it's not really labeled with anything. But what that would be dp dt, feet per second, because that's your change in your ladder. So maybe I should have made it an L, but whatever. So dp dt. So looking at this, I've got a moment, so I know when I want it to find it. I've got variables for the 2 parts missing. I do have this 13 for that ladder, and that's not going to change. I have one related rate that I know, and I have the one I'm looking for written down over here. Okay, so when I go to put these together, I go, all right, what relates P, B, and in this case, I have a 13. Again, we don't worry about the related rates yet. And I'm like, oh, that looks like a right triangle, so this probably is Pythagorean theorem. Okay, so I can start it as P squared plus B squared equals 13 squared. Now, one key thing, and you're going to hear Miss Marshall and I both say this a lot, you can only plug in what we're going to call fixed, I'm going to say values. I don't want to say lengths because not everything's exact length. It might be an angle. So fixed values right away. Sorry, so that's why the 13 could go in here and not the 5. The 5 is our moment in time that we're going to use at the end of like, where am I at? But right now, the only thing that's not changing is 13. P is changing, B is changing. All that stuff is not fixed except for the 13. Okay. All right, so I start taking my derivative. So I'm like 2p, derivative of p is dp dt. Okay, b squared, so power out, power down, db dt, and my derivative of 13 squared is 0, because that's 169. 169 is a constant. Derivative of a constant is 0. Okay, I go plug in what I know. So I know dp dt is 4. So I've got 2, I do know p, because now I can plug my moment in. So that's what I meant by right away. Now that you're finding this exact moment, now that 5 can go in for p. So this is 5. This would be, now I noticed that I've got an error, and I probably should have done this at the beginning here. I'm going down, which means this is negative, because you're getting small, like that side is getting shorter. So you should have a negative derivative. Okay, plus 2, I don't know b. I want to know dB dt equals 0. Okay, and so I notice I'm like, oh wait, I don't know b. I don't have a number for b. Well, that's where we go back and we look at our initial plugin. Now my moment in time can go in, so now I can have 5 squared plus b squared equals, I'll just make it a number, 169. Okay, so solving that, you get that b is 12. So that thing is really 12. So I would have 10 times negative 4 plus 24 dt equals 0. Solving for dB dt, then you get 40 over 24. But that was, so if you, this is 40, negative 40, so you'd add it over, divide by 24, which equates to 5/3, which back over here was the second option on there. Let's try another one. Start this one the same, try to read it, try to write down variables, try to write down what you're looking for. The setup is usually the harder part on these versus the solving and the derivatives, because you guys have been doing a lot of implicit. So hit pause, try it, and then hit play. All right, it says the radius of a circle is increasing at a rate of 2 inches per second. So radius of a circle, I'm going to use r. It's telling me the rate, so which means that is telling me dr dt is 2 inches per second. And since it's increasing, I'm going to leave it positive. Okay, what is the rate of increase of the area? Okay, now that's my question, so I'm going to put it over here. So I want to find dA dt at the instant when the area, so I'm going to write moment, so that I know that this is not fixed. The moment is when area is 25 pi. Okay, so I got all this stuff. Okay, it's talking about circles, so let's draw a circle. This is my picture. I know on my picture I've got r. I'm talking about area. So the thing that relates all these things described is your area formula. So pi r squared. Okay, now I'm looking for dA dt, and I notice I have an a here. So so things are already set up. I don't need any more writing of anything. I can just take my derivative. So the derivative of a is dA dt. Now in this case, like pi is just a constant, so it stays. 2 or r squared would be power out, power down to 1. But I would also get a dr dt because it's not time. Anything that's not time, and you won't have time in there, gets its own implicit differentiation, or d whatever dt. Okay, now when I look, I've got dr dt. This is what I want, but I need a radius. So now your moment your moment in time comes in, and I want to know what's my radius at 25 pi. Well, pi r squared equals 25 pi. So my radius at this time is 5. So dA dt is, I'm going to just reorder a little bit, 2 pi 5, and then this was 2. Okay, so simplifying that out, you get 20 pi. And now it would be in inches squared per second, because your rates, I'm sorry, because you had 2 was in inches per second, radius was in inches, so that's what the inches squared came from on there. Okay. All right, hopefully these kind of started to get the idea. We're going to have you try a few. So what do we got? 7 of them. A lot of them are very similar to ones that we just did, so hopefully you wrote notes down as you went. And then as we continue through these, we'll kind of add some more examples. And it's just examples. There's no like magic, here's your format for everything, and here's more theorem. Like it's just a bunch of examples. And they take practice. So try these problems, have things written down, don't erase, meet with others, see what they're thinking and how are they doing them. Write down questions. You know, if we were face to face, what Miss Marshall and I would do is if you're like, I don't know how to do number 3, I would come to your paper and I'd be like, okay, what do you have written down? And if your paper was blank, we would both say, okay, read the problem and write some stuff. Like you can dictate what's going on here and see, like you can draw a circle and label and get some variables. That's where you start. That's how this whole process and every one of these started was, what's the picture? What's some variables that go with that? What's described? Write some D, whatever DTs, you know, start doing that. So for all of these, you want to go do those even maybe before you meet with somebody else to go over this stuff. All right, I know today was a little longer, but I wanted to go kind of slow and give you some time to like hear me really talk through these problems. And so we'll get back on this on the next day we talk about them.